So day 2, the only difference between day 2 and day 1 is in day 2, the region you're integrating is not a rectangle. So let me draw a picture of day 1 again for you real quick, okay? In day 1, you can think of it this way. Here's your axes, right? There's this rectangular region on the xy plane. You're integrating from A to B in the x direction and from C to D in the y direction. See? And above this red shadow is the surface. So up here maybe. And somebody asked, well, how is this any different from what we were doing with Play-Doh earlier in the year? The difference is the top of this is no longer flat or even predictable. It's just governed by a function. So it's z equals f of xy. It's your mountain surface, if you like. So it's a little more complicated, I guess, than the Play-Doh stuff we were doing earlier in the year. So the way I decided I was going to teach it was I was going to draw one little tiny pillar in here. It's just a tiny portion of your volume. And we said that this distance is like dx, and this distance is like dy, and this distance is like z equals fxy. So that the volume of this thing is just length times width times height. So let's do z first. Let's do z times dx times dy. And we said there are many columns like this. If you hold your y constant and integrate into the x direction, you'll create a whole row of these pillars.
Is it squiggly?
The top is.
No, I mean the, sorry. I don't know the actual term. From the deep, as in when we were 6 looking one, back to 6? Or is it actually that deep?
Oh, this is just a regular differential. This is not a partial differential. That's a good question. So what I'm going to do is integrate from a to b, like this. Integrate from x equals a to x equals b on both sides. Like this. And you can see this is not going to give me the full volume, but it does give me one sheet of constant y here. And then we can integrate the sheets together into the y direction by going from C to D. So we just put on one more integral, and it collects sheets in the other direction. It's very clever, really. So now we're going to put on another integral, y equals c to y equals d. And then this is now on the inside, x equals a to x equals b dv. The right side looks like this, y equals c to y equals d, x equals a to x equals b. And then you have z dx dy. So you've integrated both of the dx and the dy to compile this full solid, and you've collected the sheets and the columns. Columns first, then sheets. This is my preferred way of teaching it. It does require me to write just integral symbols, just sort of slap them on there, which some people don't like. They don't like it when I teach it that way. It bothers them that I use it that way. But it turns out it's a pretty good way to understand. Okay, so that's a c at the bottom there, y equals c. A little hard to see, sorry. But one thing that's real gracious and forgiving about these is because the red region is a rectangle, if you accidentally get your limits mixed up and you put the x equals on the inside, or it might not matter too much. Like if you accidentally integrate dy first and then dx, or dx first and then dy, there's no difference at all. It's kind of like partial derivatives. I don't know if you remember, I commented that f sub x sub y is the same as f sub y sub x. The partial derivative with respect to y of df dx is the same as the partial derivative with respect to x of df dy, almost always. That's kind of true here too. You can mix up the order. But if the base of the solid is not a rectangle, then you have to be much more careful. Okay? There's still two ways to set up a problem. You can do x first or y, but the practical side of it is different. Okay? So let me just show you an example here of how you might handle this. Let's say that you had a problem that says, find the volume bound by the surface z equals e to the negative x squared, and the planes z equals 0, which is really just the xy plane, x equals y, y equals 0, and x equals 1. You might say, this is a ridiculous problem. Well, z equals negative x squared is a mountain shape of its own. Okay? Like it's a surface, it's a mountain, right? Z equals 0, this is just the xy plane. Right? Let's see if we can draw this. Let's do our y this way. You do not have to have detailed drawings, just enough to kind of grasp the basic idea. There's this mountain, okay? We're going to study underneath it, but above the ground. So the xy plane is like the ground. That's the z equals 0 plane. Okay, so above this ground, I don't know how much shading you want to do. So above this ground, but below the surface. You see? Also binding this region are the plane x equals y, which really just looks like this. This is the x equals y plane. It looks like the y equals x line down on the trace. This is the line y equals x right here. But it's a full sheet, remember? Y equals 0, that's just this plane right here in blue. That's the y equals 0 plane. And the x equals 1 plane, that's just this plane. So I think what's going on is there's this little purple region in here. I don't know if you can see it or not. But there's this little purple region. And the surface is sort of a cap on top of it. So it's like there's this triangular prism. I think I can actually draw it pretty well. So we have this triangular prism shape. But the top is some kind of a weird surface. That's what's going on. We're trying to find the volume of this. So it's all very, very wordy, but simple concept. The truth is, nobody ever draws this stuff. You really only draw the bird's eye view. Okay? So let's draw the bird's eye view of this thing. What do you see when you look straight down onto it? Well, you see this. The x-axis is here. The y-axis is here. So this is bird's eye view. Sometimes called the phi equals 0 degrees view. You're on the z-axis looking down. The z-axis is poking you right in the eye. Okay? All right, so you're looking down, and here's what you see. You see this line, y equals x, and this line, y equals 0, and this line, x equals 1. Binding this purple region. No, our face is at phi equals 0, right on the z-axis looking us down. Don't worry about the name of the projection. Phi equals 90 is the plane we are studying, but we are observing from the point phi equals 0.
Oh, okay.
Yeah, I'm sorry, that's the observer's perspective. Yeah, good question. Okay, everyone see this little region? This is the key to the problem, okay? If you can draw your pillars and sheets here in this region, you're good. All right, so there's kind of two ways to look at this. If I take my little sample pillar to be right here, I have two options. This is where it gets touchy, okay? That little guy has area dx, dy, and it pokes out of the board at us by an amount z, right? Think of it as these markers are the pillars, okay? And they all stick out at us. So they all have different lengths depending on z. Each of their own z, they're poking out. Okay, some are longer, some are shorter. They're governed by a function. Their lengths are governed by a function. Can you guys picture that? Okay, we're going to get this one. Then we're going to integrate them side to side. So we're going to go from here to there, collecting them. That'll form a sheet. Then we'll integrate up and down to collect sheets. That's one way of doing it.
We just do 1/2.
No, we're going to choose our boundaries here. So the boundaries are going to be variable boundaries. Or we can do it this way. We can take this to be our column, integrate up and down to stack the columns to form a sheet, and then integrate left and right to get the sheets to stack. There's kind of 2 ways to do it. In other words, we can dx integrate first or dy integrate first. I think we should write them both down. If we decide to dx integrate first, which is how we normally do things, we will be integrating from x equals something to x equals something, and then there's going to be e to the minus x squared, you know, and then there's going to be a dx, and the dy integral will be saved for later, and there's going to be y equals something to y equals something. This is very important what I'm about to say, okay? This is one way to do it, but I don't think we can solve it because I don't know how to integrate this function. This is one of our functions that we don't know how to integrate. We don't know the antiderivative. The other way of doing it is to flip this around like this and write it this way with the x integral on the outside and the y integral on the inside. And this one I think I can handle. The dx, save the dx for later, see? Do you guys see why I'm saying that this integral doesn't scare me at all?
Just add a y.
Yeah, the antiderivative of e to the negative x squared is only challenging when you're integrating with respect to x. But if you're integrating this and you're treating e to the negative x squared as a number, this is no harder than integrating the number 5. What's the antiderivative of 5 dy?
5y.
5y. What's the integral of negative e to the x squared? Negative x squared dy. E to the negative x squared y. So you're treating this as a number, right? Okay, so I think we've decided we're not doing this. We just can't handle the inner function, like the inner integral. We can't do it, but we can easily handle this one. So this just told me how I'm going to stack my pillars. Which integral am I going to do first?
Y.
The y, right. So it looks like I'm going to have to stack these little squares, these are top views of pillars, into the y dimension first. Okay? That was a decision I made after the fact. Okay? So I'm going to go ahead and stack this way. What's the smallest value of y in this sheet? 0. What's the largest? Y equals x. Yes. Okay, so it looks like y equals 0 to y equals x will be my limits of integration. That's stacking squares upwards, see? All right. Now I'm going to stack sheets together. I'm going from one x to another x. Well, what's the least value of x of the purple region?
0.
X equals 0, right. And what's the largest? 1, yes. So fortunately, the sheets all range from x equals 0 to x equals 1. It's very common and normal and good to have expressions as your inner limits of integration and numbers as your outer limits of integration. Don't mix those up. You want the inner ones are expressions when you have a non-rectangular region. The outer ones are numbers. So this is actually really easy to do. What we're going to do is take the antiderivative. We're pretending that e to the negative x squared is a number, you know. Let's just kind of move this over. Okay. We're going from 0 to 1, we said. We'll save this integral on the outside for later. But this inside is just e to the negative x squared times y. And we still have to plug in y equals 0, and y equals x and subtract. So save this integral for later. Here we are on the inside. We're going to have, these are being substituted in for y, okay? And then we're going to subtract. So first we're going to make our y x. And this is going to read e to the negative x squared times x. E to the negative x squared times x. And then we're going to do e to the negative x squared times 0, which of course is just 0. So this thing really cleaned up for us. And this can be solved by a simple u sub. Let u equal negative x squared so that du is, negative 2x dx. Why don't we write negative 1/2 du equals x dx? That's what we're used to doing. Here's your negative 1/2 du. Bless you. So this is just e to the u du, and there's a negative 1/2 that popped up right there. You guys are really good at that. Antiderivative is just e to the u. Remember, it's e to the u, but u was negative x squared. So this just integrates to e to the negative x squared. And you're integrating from 0 to 1. So this gives me negative 1/2, and then it's e to the minus 1 minus e to the 0.
Wait, wouldn't it be only 1? How is there 1 for e to the negative?
No, u was negative x squared. We're not squaring the 1. First of all, this is from 0 to 1, not 0 to negative 1. And we're squaring the 1 and then negating the result. Yeah. So it's e to the minus 1 minus e to the 0. So the answer is just basically that. And that's our volume. This problem is really important because it shows us that when we put those little pillars together, we really probably should just draw the bird's eye view, unless you're Sydney and you're an amazing artist, okay? But just probably draw the bird's eye view, and you're going to stack those columns in the most convenient direction. And I actually didn't know which direction until I wrote the two integrals. First I wrote it with dx on the inside, and I realized I can't do this problem. Then I wrote it with dx on the outside, and I was like, oh, that's easy. So, there you have it.
So should we aim to just add the variable if we can for the inside? Like,
Add the variable.
okay. When you integrate just
Oh, if your function is something you don't know how to anti-differentiate with respect to x, try integrating with y first. If it's a function you don't know how to anti-differentiate with respect to y first, try integrating with respect to x first. You have the freedom to integrate in any direction you want. Choose a direction that you can handle the antiderivative for. That's the trick. I'm actually going to stop recording for this video. I do have one other example, but it's much easier. And so I'm going to send out the worksheet. It's not due till Thursday. If you need me to record one more example tomorrow, I can. But primarily tomorrow it's Q&A day. So I have a bonus.